Okay, so we have seen how a homogeneous second order differential equation, which is linear and with constant coefficients, can be solved. You look at the auxiliary equation, find its roots, and then basically you're able to write down the solution for the problem. Now in this lecture we will basically revisit this procedure, but give a slightly different way of thinking about the same thing, right? You can think of this as a the essential results would be a repetition, but it's just an alternate perspective. Okay, so the differential equation of interest is a2 d squared y by dx squared plus a1 dy by dx plus a naught y is equal to 0, right? So we said you write it as this differential operator. Think of this d's as manipulate them as if they are like regular variables, and then write it as a quadratic expression, and then whose roots we find, and depending on the roots of the corresponding quadratic equation, we were able to write down the solution, right? So where does this auxiliary equation come from, right? So another way of thinking about this is to start with the differential equation and make an ansatz, right? So you make a guess for the solution for this differential equation, and you say, suppose y is equal to e to the mx is a solution for this problem. Can we find an m such that y equal to e to the mx is a solution for this differential equation, right? So if you do this, then you see that when you take a first derivative of this, you get just m times y, and when you take a second derivative of this function, you get an m squared times the same y, or e to the mx, right? So when you plug this into this differential equation, you get an algebraic equation of this kind. You get a2m squared plus a1m plus a naught times e to the mx. So e to the mx doesn't matter, right? So because this must hold for every value of x. So basically we are interested in finding m such that a2m squared plus a1m plus a naught must be equal to 0, right? So this is nothing but the auxiliary equation, right? So it is a quadratic equation involving these coefficients, and so that's how the auxiliary equation comes up, right? And so now we can look at the three different cases. We know that a quadratic equation, the solution of a quadratic equation, there are three cases which one can consider. One is if you have distinct real roots. If you have distinct real roots m1 and m2, then no problems at all, right? So we have managed to find two solutions, e to the m1x and e to the m2x. Since m1 and m2 are distinct and real, you can, if you wish, check that y1 and y2 are linearly independent solutions by finding out the Wronskian and checking that it's non-zero. But these are distinct and linearly independent solutions. So in fact the general solution for this problem is simply y is equal to a times e to the m1x plus b times e to the m2x. So it's a linear second order differential equation, so it cannot have more than two linearly independent solutions. It has exactly two of them, and so there are these two coefficients which are arbitrary coefficients a and b, which will be fixed depending upon the initial conditions, boundary conditions, right? Okay, so the second possibility is if you have distinct but complex roots, right? So this is somewhat similar. So in place of m1 and m2, you write it as a plus or minus ib, and then you can basically, it's the same solution, but then it's convenient to pull out this e to the ax, because it is common to both these solutions. And so you can also, if you wish, write it as e to the ax times a cosine b of x plus b times sine of bx, right? So this is one of sort of many different ways of thinking, writing down the same general solution, right? This is also straightforward. And then there is a third case which is somewhat subtle, and that's when you have equal roots. If you have equal roots, then, well, they're going to be real for sure, right? So and they are going to be minus a1 divided by 2a2, right? Well, I mean, well, we have assumed that a1 and a2 are real, although, so in fact you can keep it completely general. A naught, a1 and a2 are all constant, so they can be real or imaginary if you wish, right? So that's fine. So if m1 and m2 are are equal, right? So then you have only one solution, and that one solution is just given by minus a1 divided by 2a2, right? So how do you find the other linearly independent solution, right? So we make use of the technique we discussed in the previous lecture, right? So there it was, of course, a much more complicated differential equation, right? We had, we allowed a2 to be a2 of x, we allowed a1 to be a1 of x, and a0 to be a0 of x, right? So if we could find one solution for such a differential equation, we had said how there is this method by which you can find a linearly independent solution, right? So but in this case we have found one solution, which is y1 of x is equal to e to the minus a1 x divided by 2a2, right? So we will use the same technique and then look for a second solution of this form y2, which is y1 of x times v of x. So you have v of x times e to the minus a1 by 2a2, times x here, right? If you plug this back into your differential equation, now, so you have, first we have to find dy2 by dx, which is going to be dv. You have to carefully collect all these terms. There are a couple of terms, all these factors and signs, you have to be careful. dv by dx times e to the minus a1x divided by 2a2 minus a half times a1 by a2 times v of x times e to the minus a1 x divided by 2a2. So if you take the second derivative, you get one more term, right? So you get d squared v by dx squared e to the minus a1x divided by 2a2 minus a1 by a2 dv by dx e to the minus a1x by 2a2, right? So this is so this comes from taking the derivative of this part of this exponential. So that's going to give you one of these, and the other one is going to come from taking a derivative of this part dv by dx. If you add these two, the half and half will add up to 1. So minus 1 a1 by a2 dv by dx e to the minus a1x by 2a2. Then you get one more term, which is obtained when you take the derivative of this exponential here. So v of x remains as it is, the exponential derivative, that the factor remains as it is, but you get a 1/4 a1 by a2 the whole square. So if you plug all of these terms, these three objects back into the original differential equation, then there is a simplification which comes about because of these in between terms, and then you get only three terms, a2 d square. So the second derivative in v of course remains, exponentials remain as they are, minus half a1 squared by a2 times v times this exponential plus a0 v times this exponential is equal to 0. It's a common exponential and this must hold for all values of x, so you can just remove that part, and then you collect these second and the third terms, which are really so you just get a0 minus 1/4 times a1 squared divided by a2 times v of x, right? The second term. So first term is of course just a2 times d squared v by dx squared. The sum of these two terms is 0. Now some thought reveals that in fact, because we are looking at equal roots, right? So there is a constraint imposed by the fact that we have equal roots, and the constraint is that the discriminant of this quadratic equation must be 0. And what is the discriminant of this quadratic equation? It is just minus a1, so it's b squared minus ac, so that is a squared minus b squared minus 4ac, so it's a1 squared minus 4a2 a0 must be equal to 0, right? Which immediately implies that this part, this this coefficient which tags along with v vanishes. Therefore we are left with just one term, so the equation is just simply d squared v by dx squared is equal to 0, right? And the solution for this is completely trivial. It's just v of x is equal to x, right? Which is already the solution which we have used, right? It's not a surprise because we have already seen that one solution is e to the minus a1 x by 2a2, and the other solution is x times e to the minus a1 x by 2a2, right? We have already seen this, we have explicitly verified this, but this was an opportunity for us to use a technique which we have learned, which is which is much more general than being we are applying for in this special case, but it is useful to see the same ideas but from multiple directions so that our understanding is solidified. So what have we learned from this? So when you have equal roots, we have managed to show that the general solution is given by y is equal to ax plus b times e to the minus a1x divided by 2a2, right? So we have recovered using this somewhat an alternate approach the same results for this homogeneous second order linear differential equation with constant coefficients. And we have made a distinction between three cases: when you have these distinct real roots, distinct complex roots, and when you have equal roots. Okay, that's all for this lecture. Thank you.